If you've been anywhere near tech or finance news lately, you know exactly what the big story is.
Oh, yeah.
NVIDIA, the undisputed king of AI hardware, suddenly seems to have a real challenger.
Right.
Did Google, armed with their hyper-specialized Tensor Processing Unit, the TPU, actually just land a deal with Meta that threatens to sink the whole CUDA moat?
It's the multi-billion-dollar question, isn't it?
It is. So today, we're cutting through all that noise. We're looking at the two massive stories driving this narrative. First, the huge success of Google's Gemini 3 model.
Which was a big validation for them.
And second, that explosive rumor about a multi-billion-dollar Meta deal for TPUs. Our mission here is to sort the market hype from the hard reality. Is this really the start of a market replacement, or is it just high-stakes corporate theater?
And look, when you filter out the drama, when you look purely at the architecture, the cost structures, and this is the crucial part, the business models, the conclusion is pretty immediate.
Yeah.
The narrative of a rapid, widespread move away from NVIDIA is, well, it's fundamentally flawed. We're not watching a replacement story. This is a story about increasing specialization and, some very aggressive strategic leverage.
Okay, so let's start with the tech that's grabbing all the headlines. The Google TPU. Now, unlike an NVIDIA GPU, which is a general-purpose processor, the TPU is what's called an ASIC, an application-specific integrated circuit. What does that mouthful actually mean for us?
It means it's a tool custom built for one single job, and it pretty much ignores everything else.
Okay.
Think of it like this. Your laptop is a general-purpose processor. It can write an email, it can play a game, it can run a spreadsheet.
Right, does a bit of everything.
An ASIC, like the TPU, is more like a calculator that's been built to solve only one type of incredibly complex math problem. And that problem is the huge, tightly coupled matrix operations that are the computational backbone of modern AI training.
So it's sacrificing versatility for just raw brute force efficiency in one specific area.
Exactly. So when you hear Google touting their validated superior performance per watt, they're absolutely right. The TPU is stellar at that one task. But, and this is a very large but, that efficiency comes with a huge caveat.
The architecture itself.
The architecture.
Yeah.
The TPU is not designed to be a standalone chip. It's designed to be one tiny component in a massive, tightly controlled computational complex.
And the sources we've looked at really hammer this point home. That efficiency is only unlocked through proprietary infrastructure. We're talking about massive interconnected clusters.
Yes, that's absolutely key. Its performance advantage relies exclusively on tight coupling across thousands of chips, and it does that using proprietary high-speed networking, which Google calls the optical circuit switch, or OCS.
The OCS.
You can think of it as Google's own private superfast fiber optic plumbing. It makes sure every single TPU in the network can talk to every other TPU with basically zero latency.
And that proprietary nature demands scale. I mean, we were talking about truly mind-boggling scale here.
Absolutely. The newest generation, the Ironwood V7, it's designed to scale up to 9,216 chips in a single superpod. And that scale isn't just a feature, it's a requirement. It's the only way to unlock the TPU's cost benefits. If you don't use that custom plumbing, that massive coupling,
The advantage just disappears.
it evaporates instantly.
Okay, and this is where it gets really interesting for me. This architecture, it imposes deep vendor lock-in. It's not just about buying a piece of hardware, is it?
Not at all. For any outside customer, even a hyperscaler like Meta, adopting TPUs means way more than just swapping out a chip. It means a comprehensive overhaul of their entire data center architecture just to integrate Google's proprietary rack system and networking stack.
That sounds incredibly complex.
It is, and it stands in sharp contrast to the relative flexibility you get with deploying a commodity GPU, where you can mix and match parts from different vendors.
So, to use your analogy, the TPU is like a hyper-specialized Formula One car. It's incredibly fast on the straightaways, but you have to rebuild the road, the pit crew, the whole ecosystem just to run it. If you try to take it off Google's custom track.
It breaks down immediately. That is precisely the fungibility challenge they face.
Okay, let's tackle the two news items that really caused the market panic. First, the technical validation, which was the success of Gemini 3. And second, the commercial rumor, Meta buying TPUs. Let's start with Gemini.
The Gemini 3 story is really powerful because it validated Google's whole vertical integration strategy.
Right.
They designed the model specifically for the TPU infrastructure. And that initial wave of glowing reviews, It proved that this approach gives them a massive competitive edge, specifically on cost efficiency during the training phase.
So for building a foundational LLM from scratch.
If you're doing that, the TPU is currently the most power-efficient way to get the job done.
But the sources we saw suggest a critical disconnect. Once that model leaves the training cluster and moves into the real world, we start hearing reports of performance degradation, or as the tech community so brutally calls it, enshittification.
Yes, that's a brutal way to put it.
Are our sources suggesting that Google focused so much on the training costs that they skimped on the serving?
It highlights a crucial shift in focus. During training, efficiency is all about getting the model built quickly and cheaply. But once you deploy it for mass market inference, for serving millions of user queries, the imperative shifts instantly to profitability per query.
You have to slash those operational expenses.
Right. And reports suggest that even highly optimized TPU inference isn't inherently cheap for mass consumption without making some pretty big compromises.
Meaning they have to cut corners, like aggressive model quantization, which is basically dumbing down the model. You're trading quality and accuracy for operational savings.
Exactly. So superior trading hardware does not guarantee superior cost-effective mass market inference. And that's a massive headache for every cloud provider, regardless of their hardware.
All right, now let's pivot to the noise that really sent NVIDIA's stock price tumbling. The alleged multi-billion-dollar deal for Meta to purchase Google TPUs for its own data centers by 2027. What does this really mean?
This is where we have to apply a very strong commercial reality check. The rumor of Meta buying TPUs outright is, well, it's considered commercially implausible, bordering on ridiculous.
Why?
Because TPUs are strictly proprietary. They're only available via leasing through Google Cloud Platform. They are definitively not for sale as bare metal components.
And if Google were to suddenly start selling billions of dollars of its crown jewel chips directly to a massive competitor like Meta, how quickly would that just destroy their own business model?
It would be a highly destructive shift in strategy. Google's whole advantage in the cloud wars hinges on offering specialized hardware that you cannot get anywhere else. Selling TPUs directly to Meta would immediately and severely erode GCP's infrastructure moat. It makes zero business sense for Google.
So if the chips aren't for sale, what was this rumor actually about?
The consensus is that this rumor was a classic strategic leverage maneuver. It was engineered by Meta. They're using the perceived threat of a competitive architecture to put pressure on NVIDIA. Meta is basically signaling, hey, we have options. You need to give us better allocation, you need to give us more customization, and you can give us better pricing on your next-gen hardware. It's negotiation theater.
That makes sense, but wait, why go through all that effort? Doesn't that risk alienating NVIDIA, the partner they still rely on so heavily?
That's a great question, and it just shows you the desperate position these hyperscalers are in. The GPU supply is tight, the prices are high, lead times are long. Meta's making a calculated risk. They believe the leverage they gain by creating fear and doubt about NVIDIA's dominance is worth temporarily irritating them. Because at the end of the day, NVIDIA needs Meta's wallet just as much as Meta needs their chips.
And Meta's actual commitments, they completely contradict any idea of a wholesale replacement. They are committed to having compute equivalent to nearly 600,000 NVIDIA H100s by the end of this year. That's not a winding down strategy?
Absolutely not. What Meta is doing is something the sources are calling strategic triangulation.
Okay.
They use NVIDIA for general-purpose training. That's the standard. They use their own internal custom silicon, the MTIA, for high-volume, low-cost inference, like running their ranking systems. And they're likely interested in renting TPUs, which is the credible part of the rumor, to evaluate very specific features, namely the Ironwood V7 sparse core, which is designed for the ultra-large embeddings used in ranking models. Their interest is surgical. It's not a fleet replacement.
Okay, so if TPUs really do offer genuine power efficiency advantages, especially with energy costs skyrocketing, why aren't more companies just biting the bullet and making the switch? The analysis suggests the real reason isn't the hardware at all, it's the software.
This is the CUDA moat, and it's the core structural advantage that no ASIC, no matter how efficient, can really overcome right now. CUDA is NVIDIA's proprietary software layer, and it's been the industry standard for over 15 years.
Explain that for us simply. Why is CUDA such an insurmountable barrier?
Think of the CUDA moat like Microsoft Windows back in the 1990s. It wasn't necessarily the best operating system, but it was the one that everybody built their applications on.
It was the standard.
It was the standard. Every major machine learning framework, like PyTorch, every research paper, every optimized library, and crucially, every engineer's expertise is written in or deeply tuned for CUDA.
So the switching costs must be astronomical.
The operational risks and the prohibitive costs of migrating existing massive production pipelines from the CUDA environment to the TPUs XLAJX environment are just. They're massive. You're talking hundreds of millions of dollars in engineering time, debugging, the risk of critical system downtime. That cost completely wipes out any immediate hardware savings.
And that brings us to the staffing constraint. You can have the best hardware, but if no one knows how to code for it,
It's useless. Precisely. The talent pool skilled in CDA optimization is enormous and mature. You can hire a million engineers who know PyTorch and CD inside and out. The number of developers who are truly proficient in XLAJX for TPUs is a tiny fraction of that. If you switch, you are instantly limited by the availability of specialized, expensive talent.
let's talk about the architectural difference that really ties into this software lock-in. General purpose versus specialized. NVIDIA GPUs are fully programmable processors. They offer high versatility across AI, computer vision, scientific simulations. They're fungible.
Correct. The TPU, with its systolic array architecture, is optimized solely for dense matrix operations. It is brittle. If your workload deviates even slightly from that very structured, predictable data flow, say you introduce a custom kernel or a sparse data set, the TPU's efficiency just crashes.
That's the fungibility gap you mentioned earlier. In a massive data center, hardware flexibility is everything. You need to be able to repurpose hardware based on demand. You can shift an NVIDIA GPU from training an LLM in the morning to running a weather simulation in the afternoon.
A TPU is much, much less flexible. It's stuck doing what it was built for. And that lack of versatility adds long-term strategic risk. And, maybe most importantly, the maturity of CUA ensures that virtually every major AI breakthrough happens on NVIDIA GPUs first. It allows researchers to experiment freely without worrying if their custom code will even run. It's the center of the AI universe.
Okay, before we wrap up, we have to talk about total cost of ownership, TCO. Is the TPU really cheaper? We hear so many conflicting claims, especially on power consumption.
The TCO advantage is real, but you have to look beyond the sticker price. The TPU's genuine advantage is its superior power efficiency, its performance per watt. And this is vital because power and cooling, or P&C, have become the industry's biggest operational bottleneck.
Right, they're running out of power before they run out of space in the data center.
Exactly. And the comparison is stark. An NVIDIA H100 can consume up to 5 times the power of a single TPU V5e chip. For a company running millions of chips, that massive reduction in power load is an existential cost saving. That's what excites data center architects about the TPU.
But when a CFO looks at TCO, they see the hardware discount. When an engineering VP looks at TCO, they see the cost of retraining 1,000 developers and rewriting 5 million lines of code.
Exactly. And the problem with current cloud pricing is that it's highly misleading. Google Cloud maintains deliberately inflated prices for competitor hardware, so comparing their on-demand price for an H200 versus a TPU isn't a true market comparison. And any honest TCO model has to account for those massive switching costs. When you factor in the engineering salary required to jump the CUDA moat, it completely wipes out any immediate hardware savings.
So if we synthesize all of this, the specialization, the supply chain maneuvering, the software lock-in, what's the core conclusion? Is the war over?
The conclusion is that the competition is shifting away from a winner-take-all fight for dominance, and it's moving towards functional market segmentation. They're settling into their own distinct lanes based on what their architecture is best suited for. It's coexistence, not replacement.
So what does that look like long-term?
Well, first, NVIDIA will maintain its position as the premium, high-margin provider of general-purpose hardware for frontier AI and research simply because of the CUDA moat. Second, Google will solidify its position as a vertically integrated cloud provider, using TPUs as a strategic differentiator to capture the market that needs maximum power efficiency for highly structured, predictable workloads running inside GCP.
This has been fascinating. So the market shock was driven by this idea of an outright switch, but the reality is just so much more nuanced and strategic than that.
It always is.
So here is the key takeaway from this deep dive. The ultimate winner in this TPU versus GPU competition is not the company that builds the fastest individual chip. It's the entity that provides the most flexible, cost-effective, and operationally reliable platform for the most use cases. And right now, despite the efficiency challenges, that flexibility lies squarely in the software ecosystem that NVIDIA pioneered.
And that raises a really important question for you to think about. The best defense against vendor lock-in isn't just betting on the specific piece of hardware, whether it's a GPU or a TPU. It's investing in ML software stacks that allow models to be easily compiled or ported across different architectures. That focus on software flexibility is what truly reduces strategic risk and mitigates those huge switching costs we discussed today. So, what new compiler agnostic frameworks will arise in the next 5 years to truly challenge ZUDA moat? That's what we should all be watching next.